COVID. Buli omu talina bigambo. Era twebaza bwebaza Mungu kubanga febe yalekawo yamanyi lwaki naye COVID yali atutwalaganya. Good afternoon. Where are the rest? So previous lesson we had introduced the CRO. We talked about the sawtooth voltage. We also talked about the root mean square value, which can be got from the peak value out of √2. And this can be derived from the alternating current circuits concepts. So let's have an example. The gain control of a CRO is set on 0.5 volts per centimeter and an alternating voltage produces a vertical trace of 2.0 centimeters long with the time base of. Remember, we talked about a time base, which is a circuit in the X plates. The time base of. Find the value of the root mean square of the applied voltage. Find the value of the root mean square of the applied voltage. So we're going to see how this can be done. So if you look at the graph, voltage against time, it's a sinusoidal curve. So there is some knowledge which is coming from alternating current circuits. I don't know whether Mr. Kasachi had taught you AC circuits. Oh, he had not yet started.
Yeah, started.
Okay. So the length is 2 centimeters for the peak to peak. Then we have the voltage gain of 0.5 volts per centimeter. That means 1 centimeter produces 0.5 volts. So 2 centimeters will be equivalent to 2 times 0.5 volts. And this will give us 1 volt. So this length of 2 centimeters corresponds to 1 volt. And with that, it means the peak-to-peak voltage. The peak-to-peak voltage is actually 1V. So if the peak-to-peak voltage is 1V, what is the peak voltage here? There is V naught here. There is a negative V naught down here. Remember that V naught and this other V naught, when you add them together, you'll end up having 2V naught. That 2V naught is equal to the peak-to-peak voltage. Therefore, the peak voltage is going to be 1/2 volts, which is 0.5 volts. So if the peak voltage is 0.5 volts, then the root mean square value of the voltage, which is applied, will be the peak voltage out of √2, which peak voltage is going to be 0.5 divided by √2, and the answer is 1/2 √2 volts. When you simplify with the calculator, what answer do we get?
0.3535.
0.3535, which is approximately 0.354 volts. The second number, I'm going to send it via WhatsApp so that I don't waste much time writing down. Here we can screenshot that. So here is our second number. The CRO has its sensitivity set to 10 volts per centimeter. If it is 10 volts per centimeter, it means 10 volts per centimeter implies that 1 centimeter is equivalent to 10 volts. A sinusoidal input voltage is suitably applied to give a steady trace with the time base switched on so that the electron strikes. The electron beam takes 0.01 seconds to traverse the screen. If the trace seen has a peak-to-peak height of 4 centimeters, so the length is 4 centimeters, we need to find out the voltage that corresponds to 4 centimeters and contains 2 complete cycles. Find Roman 1. Oh, I didn't put the questions. Roman 1. Find the root mean square value of the input voltage. Root mean square value of the input voltage. Then 2, frequency of the input voltage. Frequency of the input voltage. So can we get the voltage which corresponds to 4 centimeters? 4 centimeters will be equivalent to 10 times 4 volts. And thus 4 centimeters are actually producing 40 volts. So the true peak-to-peak voltage is 40. This means the peak-to-peak voltage is 40 volts. Therefore, remember peak-to-peak voltage is 2 V naught is now equal to 40. Therefore, the peak voltage is 40 divided by 2 volts, and this is actually 20 volts. So if the peak voltage is 20 volts, we need to find the root mean square value of the voltage, which is got from V naught out of root 2. And this will give me 20 divided by root 2. With this V root mean square, we can compute this with a calc and get the answer. Someone has an answer, which is 14.142 volts. And the second question says the frequency of the input voltage. Remember, they have said, let me see, what have they said? It has 2 complete cycles. So 2 complete cycles, 2 cycles, the time taken is equal to 0.01 seconds. So 1 complete cycle is equal to 0.01 divided by 2 seconds. So time to make 1 complete cycle, remember, is the period. So when you divide this, what you get? You will get 0.005 seconds. But now, if this is the time, this time is the what? Is the period, the time taken to make 1 complete cycle. Frequency is got from 1 over the period, which is 1 over capital T. Therefore, frequency would be 1 all over 0.005. Someone can compute and get us the answer. This is the same as 1 over 5 out of 1,000. And this is actually 200 hertz. Now, this last number 3, you're going to try it out. Now, give me some of the hints of what you've done.
Excuse me, teacher.
Yes, please.
Teacher, I was asking this part after peak-to-peak voltage equals to 40 V. Why are we having 2 V naught equaling to 40?
Okay.
Yes.
On the curve, the curve looks like this. You remember the curve I drew last lesson? We have a peak value there. We had another peak value down this way, negative V naught. Okay. So when the sine curve is produced, It goes to the peak there, comes down to the peak again, goes back to the peak up like that. Yeah, then it continues. For this very example, the first cycle is here, the second cycle is here. Because this is time t, it has taken a time from here up to here of 0.01 seconds. Now, because of this length, the peak-to-peak length was 4 centimeters. Okay, yet the PD produced at 10 volts per centimeter. Now, the peak-to-peak voltage, the voltage from 0 up to V naught is V naught. Also, from this 0 up to this other lower peak is V naught. So when I add the two, yeah, you'll get V naught plus V naught as the total voltage from one peak to the other as 2 V naught. Now, the 4 centimeters, find the corresponding voltage to it. The corresponding voltage was 40. So it means the 4 centimeters corresponds to 40 volts, yet the 40 volts are the peak-to-peak voltage. So the peak voltage from V naught up here to negative V naught is actually 2 V naught, which is equal to 40 volts. That is how I ended up getting the peak-to-peak voltage as equal to 40 volts, and finally the peak voltage became 20 volts. Have I made more sense?
Thank you, teacher.
You're welcome. So can people try out the next number? I've already sent it on the group so that we finalize cathode rays. So that's the end of cathode rays. The rest is just for you to read ahead and read advancedly from the internet, from textbooks, anything that comes along with X-rays. Otherwise, today I'm ready to introduce what we call the Bohr atom when you finalize that example. Those who get answers, put them in the chat so that I can take a look. Sam, oh my God, is just coming in. Who has got the amplitude on that next number? Of course, the amplitude they're asking for the peak value. Get it.
I know, you are thinking very hard.
Mm. Five at least, or some 10. We have them here. So that whoever visits us is like, man, these guys.
How much is this?
You can get at 500.
Yes, 500,000.
Mm.
That world is upside down. These are things you should have. We should have. They are no longer like having a good food.
Yeah.
It is no longer just a luxury.
You must have
You
one.
must have a good phone.
If you have, yeah, I sent for a new phone. This one was mixing me, and I sent for a new phone.
Which one did you send?
That one. I had one some boy stories. It was working for me, so I sent for a new phone.
Exactly. This is the phone.
Sent for a new phone and it's doing for me wonders.
This is the one.
Yeah, even has a sound sensor here for security. Don't waste time opening so much.
And you have been a man of Sony. I have been
Yeah, I
very,
had a
very
Sony,
attentive.
yes. Yes, the one who's not online on the WhatsApp group, here is the number. Then those of you who don't have the question, there it is. Let me wrap up this part so that we can have everyone seeing the number very well. 900 abroad. Right, first hand. Sure. The question began from here, whereby a CRO with the time base switched on is.
Just relaxing. I didn't know that. I didn't know you're teaching the whole country. I'm sorry.
Is connected across the power supply. The waveform in the figure below is obtained. So this is the waveform which was obtained. The person doesn't have WhatsApp. That's the question. So go ahead. Has anyone got the amplitude yet? The amplitude, of course, they're asking for the peak value. The amplitude is this one. Someone has got the answer, you let me know. Let me first add these people who are not on WhatsApp. Anyone with a peak value? No one has sent me a message. Okay. Perhaps all of you are there. Someone with an answer? Saulo weapon, correct. Hammered none, wrong. Hammered none, try it again. But Saulo weapon, what is your name? Saulo weapon. How do you read your name, mister? Saul weapon. Who can name? Can your parents name you Saul weapon? Saul weapon has got the correct answer. Yam Adnan has the wrong one. Yes, please. Saulo, proceed. You have the correct answer. The rest also try out and give me the peak value of voltage or the amplitude of the voltage. Girls, you're too quiet. What's happening? Hey, where are people going? When you ask for solutions, people run away. That's not fair. Ani, Saulo weapon, how come you're not arriving also anymore? Since they told us we had 5 volts per centimeter, it meant 1 centimeter is equivalent to 5 volts. Now, because they said each line was representing 1 centimeter, Each line was representing 1 centimeter. These are 2 centimeters. So 2 centimeters are equivalent to 5 times 2 volts. Therefore, 2 centimeters actually produce 10 volts. So the peak voltage is 10 volts. Or the amplitude. They say the amplitude of the voltage. This is the amplitude of the voltage. The voltage gain. Calculate the frequency of the power supply if the time base setting is 5 seconds per centimeter. 5 seconds, okay, who is this one? Teacher, are the lines we are to count vertical? Hey, here, Madina, your question is, I don't know. What I wanted to say is the question said the distance between each line is 1 centimeter. So you can count 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters. If one wanted to use 2 V0, you'd say 2 V0 is equal to 4 centimeters, meaning V0 is at 2 centimeters. So look for the voltage of 2 centimeters. Voltage corresponding to 2 centimeters we have seen is 10 what? It's 10 volts. So V0 is 10. Calculate them. The second one, they have said 5 times 10 power negative 3 seconds per centimeter. It means 1 centimeter takes 5 times 10 to the power negative 3 seconds. Now, because of the cycles given, the first complete cycle is here, the second complete cycle is here. It means we have 2 complete cycles. So if you have 2 complete cycles, what does that mean? It means that each cycle covers how many centimeters? According to this diagram, they said each line, you have the distance of 2 centimeters. 1 centimeter, 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters. So the total distance here is what? Is 4 centimeters. So that means 1 cycle is 2 centimeters. 1 cycle is equal to 2 centimeters. And therefore 2 centimeters take how much time? 2 centimeters take 5 times 2 times 10 power negative 3 seconds. Meaning 2 centimeters are producing 1 times 10 power negative 2 seconds, which 2 centimeters correspond to 1 cycle. So the time to make 1 cycle is a period, which period we have seen is 1 times 10 power negative 2, and thus the period is 0.01 seconds. Because they asked for the frequency, frequency is got from 1 out of the period, which is going to be 1 out of 0.01. And the answer is going to be frequency is equal to 100 hertz. Now, because we have 2 cycles, this is for 1 cycle. Because we have 2 cycles, the frequency of this power supply will be equal to the 2 cycles times F, which will give us 2 times 100, and thus we shall have 200 hertz. The reason why we are saying we are having 2 cycles is because from here up to here is 1 cycle. Then from there up to there is another what? Is another cycle. Okay, so with that, that is how you have to look at that number. When I saw people running away, then I wondered. So one of the second last topics here is quantization of energy and energy levels. And the other one will be Milkan's oil drop experiment. I think I talked about the Bain-Bridge mass spectrometer. So when I finish those two, shall have finished the entire syllabus of modern physics. Apart from those who came in late, those ones would have missed, then we shall be forced to review some of the areas as we discuss numbers and discuss papers, if time allows. So today, how much time do we have? We're supposed to finish at 4:30. Okay. Screenshot that. I go to the next page. Let me press the next page, new heading, new page, which is going to be called quantization. Of energy. Quantization of energy and energy levels. And energy levels. And in this, the first definition we talk about is what we call the Bohr's theory. Bohr's theory of the hydrogen atom. Bohr's theory of the hydrogen atom. Now, Bohr is one of the few people who have made it a point to talk about atoms and their structure. Though one of the challenges is that Bohr talked about mainly the hydrogen atom. And we shall see that some of his challenges with his theory is that he talked about only an atom which has a single electron. He did not specify more about atoms with many electrons. But among his predictions, he predicted that electrons revolve around the nucleus of an atom, which is correct. And then he also predicted that when electrons are in those orbits, they do not emit radiation. But when they make a transition from one orbit or from one energy level to another, then they can emit radiation of energy, which is equal to HF. So with those predictions, Bohr's theory came into existence, as we are going to see. So one should know what Bohr suggested. And if you get to know what Bohr suggested, then you can use his postulates. We normally call them postulates. And then we end up seeing what exactly. Teacher, maybe in case of the, always in the future, I request to review photoelectric emission because I joined late. Okay, we shall review. We shall review all the areas people want to review. We shall agree that we review these areas, these ones, and then we review. So, a Bohr atom is which atom? A Bohr atom is a definition which is, I think, the longest in physics we have at your level. And we can say it's an atom with a small central positive nucleus, with electrons revolving around it, only in certain allowed circular orbits. And while in those orbits, the electrons do not emit any radiation. But when an electron makes a transition from one energy level to another, it will emit radiation of energy, which is equal to HF. Or change in energy will be equal to HF as a result of the difference in the different energy levels. For example, energy E2 minus energy level E1. These will represent the energies in the different orbits and in the different energy levels. So the definition, I will send it and you'll see it in the notes as we shall see. But let me first send some of these items here so that you can have some of them with you. Now, going back to borrow more knowledge from the what? So by definition, we can say a Bohr atom is one with a small central positive nucleus with electrons revolving around it in only certain allowed circular orbits, and while in those orbits, the electrons do not emit radiations. So you'll add on that, but when an electron makes a transition, okay, that one you can leave it out. Then among his postulates, one, he suggested that electrons revolve in only certain allowed circular orbits, and while in these orbits, they do not emit radiation. What did he mean? If this is the positive nucleus, and we have orbits where the electrons revolve about the nucleus, when these electrons are revolving around the nucleus, they are in specific orbits. An electron is in this orbit, an electron is in that orbit. We have electrons here in this other orbit. We have also electrons in this other orbit. So while electrons are in these orbits, they do not emit radiation. And the higher you go, the more energetic these electrons are. This one has a greater energy. For example, if this is orbit with energy E1, this is orbit with energy E2, this is orbit with energy E3. It means energy E3 is greater than energy E2, is greater than energy E1. Just like the way we have the solar system. Someone one time said, what if the Earth, the sun, they're all enclosed within a very big atom? Because the way the planets revolve around the sun, it is exactly the same way how electrons revolve around the sun. I mean, electrons revolve around the nucleus. In that sense, we don't have scientific evidence for that, but someone was assuming, what if it's that way? In that regard, when these electrons are in orbits, like I've said, Bohr suggested that they revolve in these orbits. They are certain because this electron has less energy, while this one has greater energy. That's why it's a little bit further away. Then this one has more energy. Whereas if the electron has the maximum amount of energy, or it has undefined amount of energy, it has so big energy, it will escape and run away from the atom. Yeah? More of that can also be talked about when we looked at the line spectrum and continuous spectra in X-rays. When an photoelectron came, or X-ray photon hit the electron deep inside and gained energy and displaced it, that electron could gain energy and escape totally and never come back to the atom. And by that, a transition would be made and the line spectrum would be formed. Even here, we shall talk about the line spectrum. So when the electrons are in these orbits, they don't emit radiation. They can only emit radiation once an electron has made a transition from one energy level to perhaps this other energy level. When it is leaving here, the difference in the energy levels corresponds to change in energy, which energy is HF. So that is the first definition or postulate he suggested, that once electrons are in certain orbits, they revolve around the nucleus, but as they revolve, they do not emit what? Radiation. The second one, in allowed orbits, the angular momentum is an integral multiple of wavelength of n over 2 pi, not wavelength. Wavelength is for X-rays. So the second one is said, angular momentum is an integral multiple of nh over 2 pi. What do we call angular momentum? If this is the positive nucleus, and this is the electron revolving around the nucleus, this electron revolving around the nucleus has a distance r from the nucleus, but as it revolves, it possesses momentum. So the moment of momentum about the center, the perpendicular distance of the moment from the nucleus, will give us a moment of mv, a moment of the momentum, which is mvr. So mvr is an integral multiple of n out of nh out of 2 pi, where n is the principal momentum, I mean quantum what? Quantum number. So therefore, that is the second postulate of Bohr. So, welcome, salam. So the second prostrate, like I've said, is predicting that in certain allowed orbits, the angular momentum is an integral multiple of nh over 2 pi. Then he also has a third prostrate. When an electron makes a transition between orbits, which I've already talked about, yeah, electromagnetic radiation of definite wavelength is produced. This electromagnetic radiation, we said, is a result of the change in energy at the different energy levels. And according to those notes, you will see that he will predict that the change in energy is equal to HF, which HF is E2 minus E1 is equal to HF, which is HC over lambda. I think this is familiar. So they can ask you for the wavelength of the radiation emitted when a transition has been made. Then lastly, the fourth prostrate talks about, fourth prostrate is here, talks about in certain allowed orbits where the angular momentum is an integral multiple of h over 2 pi, the energy is a constant. What does that mean? It means that all these electrons in this orbit, they have the same energy because their energy level is E3. It means whoever is in E3 possesses energy E3, so they have a constant energy. Just like you're in senior 1, you're in senior 2, you're in senior 5, you're in senior 6. Your cutting points are the same. The energy you all have to put in is the same. You want to go for government sponsorship, you want to go for electrical engineering, you must get 20 points with an A in physics. Yeah? If you're a girl, at least a B. Okay. So if you're lucky, if that is the cutoff point or that is the cutoff range, then it means whoever does not possess that capacity of getting an A in physics will not qualify for electrical engineering. So because all of you want to go for electrical engineering, you all have to score the same. So you all possess the same cutoff. You have to put in the same amount of energy in terms of performance. So Bohr predicted that every electron in a given energy level, they possess the same constant energy in that energy level or in that orbit. So in that orbit, everyone has the same amount of energy. Before I proceed, do we have some questions? Yep. Any questions?
No question.
Are we all understanding very well? Because this concept requires understanding. It's not a very complicated concept, but it's a very understandable and very interesting area of advanced level physics. Yeah? Okay. Now, the next definition is what we call the total energy. Having left that part, we go to what we call total energy. Of an electron. Total energy of an electron. And this one can be checked. Whereby if you have an electron that is moving with this distance r from the center, the electron has a velocity v, then this electron is going to experience a force of attraction. Remember, the electron is negatively charged, whereas the nucleus is positively charged, okay? So if the electron is negatively charged and the nucleus is positively charged, you will discover that this electron is actually being in position to get an attractive force. But as it keeps rotating, that attractive force provides its centripetal force with which it moves. Those of us who have managed to attend the centripetal classes, you should now know what centripetal force is all about. the force that keeps a body moving in a circular path. So we have, for circular motion, the electrostatic force of the electrostatic force of attraction between the two charges is going to provide the centripetal force. So the electrostatic force of attraction provides the centripetal force. Now, from Coulomb's law, you know the force of attraction is Q1, Q2 out of 4 pi epsilon r squared. I think you remember. So, but because these charges, if you were to look at these charges, you'll find that the charge on an electron, because it's a hydrogen atom, it has how many protons? 1 proton. It also has 1 electron. So the number of protons and electrons are the same. But the proton has the same charge, which is supposed to be NE, but N is 1. So it will be giving us charges as E out of 4 pi epsilon r squared. Reason, we are looking at a hydrogen atom which has 1 electron, 1 electronic charge for the electrons and 1 electronic charge for the protons. So this is going to give us E squared out of 4 pi epsilon r squared. So because the centripetal force is mv squared out of r, this is going to be equal to E squared out of 4 pi epsilon r squared. Reason, we have said the electrostatic force of attraction between the nucleus and the electron provides us with a centripetal force. When I make mv squared the subject, I'll have E squared out of 4 pi epsilon r. Then I introduce a half on both sides. I'll get a half of mv squared is equal to E squared out of 8 pi epsilon r. And this can be equation 1. And this is the kinetic energy of the electron as it revolves around the nucleus of the atom. So if that is the kinetic energy, we need to also get the potential energy. Now, these areas are related. The area here of electrostatics of these charges is related to the definitions in electrostatics of Coulomb's law, where we have charges, point charges. Then it is also related to the gravitational physics, where we have rotation of planets. So we have energy possessed by an electron. We also have energy or work done to move a charge in Coulomb's law. Remember work done, remember there is what we call electric potential. Work done to move a positive 1 coulomb of charge from infinity to a point within an electric field. Here we shall have also potential, which is coming as a result of work done to move an electron from infinity to a point within a given orbit of a given atom. Then in gravitational physics, we shall do gravitational potential, which will be work done to move a mass of 1 kilogram from infinity to a point within the gravitational field of a given planet. So those 3 sections, they share the same concept of physics. We just change a little. So if you understand one fully, you can easily understand the other 2, right? So I'm saying this area is going to relate with gravitational physics. It is going to relate with charges and work done in moving charges in electrostatics. And please, you need to pay attention at least to all of them. You cannot miss all the 3 when you name is setting. It is rare. You can have this one. You can have gravitational physics for work done. You can have electrostatics work done to as potential. So you have to be conversant with at least one of them, or both of them, or all of them. So for potential energy, we shall look at potential in a way that we look at work done to move an electron from infinity. Should have looked at this under Rutherford. The small change in work work done is equal to the small change in force times the distance. Is equal to force times the small change in the distance you're going to cover, whereby total work done will be equal to the integral from infinity up to a point, a distance r, of the force dr. But remember, the force is the force of attraction between the two charges, so infinity to r of e squared all over 4 pi epsilon r squared dr. Now, with this sense, you will see that when you integrate, we shall have a negative e squared over 4 pi epsilon r. Now, we are substituting this from infinity to r. When you put r, you get a negative e squared all over 4 pi epsilon r minus, when you substitute infinity, you shall get a negative e squared out of 0, out of 4 pi epsilon infinity. But 1 over infinity is always 0. So the whole of this term reduces to 0. So therefore, the potential energy becomes a negative e squared all over 4 pi epsilon r. Similar to the work done in potential in electrostatics, work done on one column of charge is 2 over 4 pi epsilon r. But now, because if you're not doing one column of charge, here we are doing e columns of charge. So it becomes, it is the same as one saying e out of 4 pi epsilon r times a negative e, because the charge is negative on the electron. This is the charge on the positive column, on the positive nucleus. So it's the same idea, but the derivation is what I've just done. And according to the notes I'm going to send you, the derivation is not there, so you will take the screenshot. So finally, total energy will become kinetic energy plus potential energy, which will confirm e squared all over 8 pi epsilon r minus e squared all over 4 pi epsilon r. And in totality, this gives me a negativity of e squared all is over 8 pi epsilon r. So total energy of an electron is always capital E, which is given by a negative e squared all is over 8 pi epsilon r. This is a very sensitive formula. We need it to derive other formulae next time, because we are going to derive energy in this form. Negative me to the power 4 all over 8 epsilon squared n squared h squared. We shall need this formula to come and arrive here. So I'm going to request you to go back and revise and prove, so that by next lesson, you know where we stopped and you can proceed without fear or favor. Now, before I invite any questions, there is always this question which is said: explain why energy of an electron is negative. Total energy. Even total energy of a body or of a satellite in space, in gravitation, also that energy will be negative. Even in electrostatic potential, that energy is supposed to. So they can ask you, explain why that energy is always negative. When we are here, we shall talk about the energy being, the electron being bound to the nucleus of an atom. Being bound, it means it cannot leave because it is negatively charged. Why? Because there is an attractive force. Now, because it is bound to the nucleus of the atom, work has to be done against the electrostatic force of attraction between the electrons and the nucleus. So the reason why that work has to be done against the electrostatic force of attraction, we are doing work against the force of attraction. That is the reason why energy is negative. Then also they can ask you why energy is negative in gravitation for a satellite. It's because when the satellite or when a rocket is going in space, the work we do, the Earth, for example, as a planet, is trying to attract the planet backwards. the planet is trying to go away. So the planet is doing work against the gravitational field of the planet. So the work it does ends up also becoming what? Negative. But when we reach there, we shall explain more about it. But for now, let's talk about only the electron, which is bound to the nucleus of an atom. And if it wants to leave, it has to break that electrostatic force of attraction. So we do work against the electrostatic force of attraction, so as the electron to be in position to move. Otherwise, if not, the energy wouldn't have been negative. So that's the reason why energy is negative. It's a very interesting topic. And I expect questions now, if I can say my time is up. Can I have some questions? Someone, please.
Excuse me, teacher.
Yes, please.
I have not understood why the energy is negative.
Why the energy is negative? Let me give you an example. If you as a lady, you fall in love with a man, and you love each other so much that you know your husband's PIN codes for the phone, for the bank accounts, you love each other and everyone is admiring your love. And then there comes a side dish. Yeah, how are they called? Slay queen. She comes and tries to do what? To break you two, to try to snatch away your man. And this slay queen is fighting hard. Everything she tries to do, you're doing it as the wife. And most so she cannot even give money to your husband, but for you, you can. Yeah? So it means she has to go and do an extra mile of work, which can even include death, or which can even include bewitching, or which can even include maybe getting you to an accident and you crash so that she can have your man. Now, when she does that, she's doing negative energy. You hear people say negative energy, whereby for you want to do something, but someone is speaking in the negative sense. They call it negative energy. The idea comes from here. It is scientists who introduced that definition in the world of English. So the negative energy means you are trying to do work or to do something which is not supposed to be done. Okay? Now, when we come to our electrons, I don't know whether you've understood that slay queen scenario. When we come to
Yes, teacher.
Okay, when we come to our scenario of the electron, this electron must be attracted to the positive ions or to the positive nucleus. Do we agree? Do you agree on that? That
Yes.
this electron has to be attracted by the positive nucleus. Why? Because the charges are opposite. Opposite charges facilitate an attraction with each other, okay? With that said, what does this call for? It means that whoever wants to break this bond, whoever wants to remove this electron from this orbit, due to the attraction it has, one has to do work. But the work you're going to do is not supporting the electron to move closer. The work is supporting the electron to move away from where its bound is. So that work you do is negative. Reason, it is against the electrostatic force of attraction between the electron and the positive nucleus. How are we?
Yes.
Yeah?
Understood you.
Okay. Any other questions? So if no further questions, allow me to stop here. Let me send the write-up so that people can make notes. Any other questions when you read ahead, please go ahead and consult. Otherwise, I don't normally get so many questions concerning what people have read and what their findings are. I don't know that it's because people are not reading enough or something. But please go ahead and do so that you become better physicists. I want you to, we are here to hold seminars with other groups. We can invite you and hold a seminar with other groups, and then we ask you to present. Okay, so we shall have this. I've also sent some ahead notes, which we shall discuss before calculations. It will be easier for me to discuss them if you already have them. Okay, with that, we can stop here.